is Professor Yong Lin from Tsinghua University. He is recipient of the Frontier of Science Award this year. And we'll talk about Analytic and Reidemeister torsion of digraph and path complex. Please welcome him.
I would like to thank the organizer to organize this wonderful conference. So this year the conference went through much better than last year's. So this work is joint work which Grigoryan, he is also here, and Professor Yau. So this is the main topic we are going to talk today. So we introduce the notion of Reidemeister and analytic torsions on the finite digraph by the path homology theory, which was introduced by Grigoryan, Muranov, Yau, and me about 10 years ago. So we used the homology base to construct a preferred base for the path components on the digraph T, which leads to the definition of Reidemeister torsions. We also defined the Hodge Laplace delta P acting on the P path and use the positive eigenvalue of delta P to define these analytic torsions, PG. So we prove these two torsions are same. And we also obtain some formula for the torsion of Cartesian product and the join of the digraph. And finally, we studied the spectrum of the Hodge Laplace on the Cartesian product of G power h power n. As a corollary, we classify the spectrum of Hodge Laplace for the cube. We know there are some different definitions for the homology on graph. For example, the Greek homologies, which use the complete subgrid as a simplicity set, and also they are so-called singular homology. However, the notion of path homology has some advantage because it enjoys some property. For example, we have this Kuhn's formula for Cartesian products, and for the join, we will talk later. And this path homology is also homotopy invariant, which is not true for the Greek homology and the singular homologies. Of course, I will not talk about this homotopy theory for digraph today, but this homotopy is a complete discrete homotopy. Also, the concept of path homology is from the concept of so-called path chain complex, which is no trivial by itself. First, we introduce what is the path complex. So path complex is defined on a finite set V. So given no negative integer P, we given an ordered sequence I0 to IP, which the P is the length of this we call the P path. And we denote this sequence as I0 to IP or E sub I0 to IP. The former, the coefficient is we use the real number. You can also use this for any feed. So the R linear combination of these elemental P paths are called P paths. We use lambda P to denote the linear space of all the P paths. Then we can define this boundary operator on this lambda P. So this is the classical definition for any P paths. So this T operator working on this P plus 1 path, we equal the right hand side. This is the sign sum. This notation means we delete this index ZQ. So this is this operator is from the lambda P plus 1 to lambda P. We require the P path is called regular. That means every consecutive index ik is not equal to ik plus 1 for any k from 0 to p minus 1. Otherwise, we call the irregular path. So we use IP to denote all the irregular paths. So then the quotient space RP is linear isomorphic to the space all the regular P paths. So we use this RP to denote all the regular paths, P paths, and we use this boundary operator D working on this this regular complex. So what is the path complex? Path complex is all this connection of this regular elemental path, which this following property. Given a p path ei0 in, we delete the first index and the last index. The path is still in the p. Then we call this this set is a path complex. That means if you delete the last one and the first index, this path is still in the collection of this set V. So all the paths from P we call the allowed paths. For example, we'll give an example. What is the P path complex? Given a digraph G, digraph means there is a direction on every edges. So the V is the weighted set, and the E is the edges set. So this notation means there is edges from S to Y, there's a direction from S to Y. So given an elemental P path, N path I0 to IN from the weighted set V, we call it is allowed if IK minus 1 to IK is these edges from IK minus 1 to IK for any K from 1 to N. So denote the Pn are all the set of all allowed N paths. So this is, for example, P node is the weighted set V. P1 is the edges set E. So clear this satisfy this path complex assumption. So this in this path complex from this definition we denote this by PG. So this is a path complex corresponding to a digraph. So we use this notation AP denote all the allowed elemental P paths. This is from the P path, not only for the digraph. So this AP is not invariant under the boundary operator. For example, for this simple graph, by definition, this is in the P2. This is a P2 path. But if we do the boundary operator, then it is become this is in P1 because there is a direct edge from 1 to 2 and 2 to 3. But this is not in P1 because there is no edge, direct edge from 1 to 3. So this simply under this boundary operator, the AP is not invariant. So then we choose the subspace of AP, omega P. Omega P is those P allowed paths, and we assume the boundary of this P allowed path is still a P minus 1 allowed path. So this set you can easily check this omega P is the D-invariant P path. So we get a chain complex for this omega P. And from this chain complex, of course, we can define this homology group. So this is the definition, the standard definition for the homology group, path homology group. This JP is the kernel of D, and BP is the image of the D. We can also introduce some inner product on this allowed path. For example, we can for the two p paths u and v. So EI is all the elemental p paths on the Rp. So this certainly is the linear space. So we can define this. This is any p paths. For these two p paths, we can define the inner products. And the first inner product we call the standard inner product, and the second one we call the normalized inner product. Given this inner product, we can define the Hodge Laplace, delta p. So this is the standard definition for the Hodge Laplacians. So where dp star is the adjoint operator of dp, which respect to this inner product of omega p. And also, if delta p u is 0, then we call this u is a harmonic element. And denote this float HP is the set of all the harmonic elements in omega p. And you can easily prove this Hodge decomposition for the omega p. This is a direct sum of these three subspace of omega p, where you can also prove this homological HP is isomorphic to this harmonic element set HP. And this just from the linear algebra you can prove this. Now we come to define this Reidemeister torsions. So use this base of omega p. So we choose a base omega p, this little omega p, a base of omega p. Then and a base HP in the homological group HP. And we can choose this representative in the kernel by HP tilde. Also, the BP is the base in the imager BP. And the BP tilde is the pre-imager of this BP. Pre-imager of BP. Then it is also, you can check, this is the base in the omega p from the linear algebra. We use this notation. Given U and W are two based on the n-dimension linear space, use this notation to denote the absolute value of the determinant of this transformation matrix from W to U. So then we can define this R torsion. We call it delta tau, which in the omega space, and given this space omega and h, we can define this definition. Well, what is this? This is the transformation. This is this absolute determinant of this transformations matrix. Compare these two base on the omega p, from p from to 0 to the n. We can prove this this torsion is not depend on the choice of this BP, and also not depend on the BP tilde and the HP tilde. So this is well defined. So this is well defined, not depend on the choice of these three base. Questions? This bracket, this means the transformation matrix from omega p to this space, these two base of the linear space. Given two base of the linear space, there is a transformation matrix between them. So, yeah, there is the determine, take the absolute value of this determinant. But if you choose the different omega and h, if you choose omega prime and h prime are also the base of in omega and h, then you can prove this formula. So this formula, if we given iota is the inner product structure in omega, and we can, then you have the inner product, so we can choose this base as also normal base. So now we choose this HP and omega p both are also normal base. Then this omega p prime and also HP prime is also normal basis. So this determine are all 1 or minus 1. So this will disappear. So then we can see these two torsions are equal. In this case, the torsion only depends on the omega and the inner product iota. So. If you give two different inner product, for example, if you given this I prime, this iota prime and iota has this relations, then we can calculate the torsion for iota primes like this in the right hand side, depend on the right hand side, depend on this constant Cp. We will all use this formula later. For example, we have used this standard inner product and the normalized inner product. This means Cp is 1 over this P. So we get this two relation of these torsions. This we give an example to compute the torsion. We know the torsion was introduced by Reidemeister in 1930s. So in the manifold, so it actually is hard to compute the torsion on the manifold, but on digraph it's easy. It's just a linear algebra. For linear algebra, you can get the torsion for any digraph. So this is a triangle. So you can write down all the omega p and also all the BP and the JP. Then from the definition, then you can get this. You choose another also normal base, and finally you can obtain this these torsions, and also. This is the torsion for the standard inner product. This is for the normalized inner product. And you can also compute the square. What is square on our setting? Sorry. This is a square on our setting. So you can also compute the torsion for this square. And you can find that this torsion is 2 times square root of 2. And actually, you can, for the triangle, these two has same homology group. And also they are even homotopy equivalent. Also, I didn't say about this homotopy, but it's easy to see from the definition. These two are homotopy equivalent. So, but the torsion is different. So this is also the initial idea from the Reidemeister. They also use this Reidemeister torsion. He also used this Reidemeister torsion to distinguish different manifold have same homology group and homotopy equivalent, but the torsion is different. So. Next, we come to define these analytic torsions. So this we need to define this so-called Hodge Laplacian. We already defined this, and this is it's easy to check. This Hodge Laplacian is self-adjoint and non-negative definite operate on omega p. So all these eigenvalues are real. Actually, it's non-negatively real. So we use this all the eigenvalue, no zero eigenvalue to define this zeta function for this Hodge Laplacians. So the analytic torsion D is which is because the Hodge Laplacian depend on the inner product. So there's inner product here. So is like the right-hand side is the definition. And you can check this. Actually, this is minus this relate to all the positive eigenvalue of this Hodge Laplacians. In this case, this graph is because we only study the finite graph, so the all the eigenvalues are finite. So this is simple. If it is manifold, this is infinite. You have to prove this is extend to manifold functions for the respect to the S. So, but in this case, this is simple. So we can prove these two definitions of torsion. They are equal actually. This is the proof of the idea actually comes from the Ray and the Singer's papers in 1971. Actually, this paper he introduced. They use this so-called Delang homology, Delang form to define these analytic torsions. But on graph we don't know what is the Delang form, so we can only use this Hodge Laplacian for the p-path. Actually, in the paper, they also introduced some kind of this combinatorial analytic Hodge Laplacian to define this T. So they prove one of these results is prove these two are equal, but they only prove it is under the case all the homology group are trivial. They introduce some representative on the fundamental group that make this all the homology group HP are trivial. But on graph, I think we cannot do that. But to modify the proof, we can still get this result. And next, I will talk about this product of the Cartesian product of this path complex. So to do this is just because for simple graph, for this simple graph, we can compute these torsions, but for the complete complete graph, maybe it's very hard to still very hard to compute. If this complete graph comes from some Cartesian product of some simple graph, then we can use this formula to compute the torsion for the complete graph. So given what is the product of these two paths? So given two finite sets, that's why you can define this Cartesian product Z. So what is the regular path on this Z, on the product set? So we skip this notation. We just use the picture. This is easy to understand. So this is a picture of this product path on the Z. And this projection to the S direction and to the Y direction, this is oranges S path and Y path. So we need this notation. We need this so-called elevations Lz is the number of the small square on under this path. Yeah. So for example, in this graph, the Lz is 27. Just count the number of this small square. Yeah. Then for given two paths P path S and Q path Y, and what is the cross product of this ES and the EY? This is equal to right hand side. It's not just one path. This is the sum for all this kind of SZ, but which is sign, given this sign. The signs depend on the elevations number Lz. So we can this is definition is for the elemental path, but we can extend to linearly to the whole space, inner space. So this is the just notation. Given a p path on S and Y, we can define the p. We can use this notation to denote the Cartesian product of the path on the PZ. What is the inner? Because our definition depends on the inner product of the space. So what is the inner product on the product space? This is the, we can check. This is the for the standard inner product. This is actually looks not so nice as the coefficient here. And but for the normalized inner product, we have this. This looks good because this is just the definition for the normalized inner product. So for the normalized inner product, we have this formula for the product space. This is important because from this inner product we can get a product formula for the Hodge Laplacians. We can first you prove this for the adjoint oblet, you have this formula, and for the normalized Hodge Laplacian, we have this product formula. This is good for us. Then use this, we can prove the, also we need some definition for the Euler characteristic for this omega space. So this is the definition for the Euler characteristic. This is the sine sum of this dimension of omega p also equal to the sine sum of this homology group HP. And we can prove if the for the product space, the torsion, this is normalized torsion, T prime is the normalized torsion. For the normalized inner product, is we have this formula for the normalized products torsion, normalized inner product torsions. So the right hand side is the torsion for the S and Y. This is the Euler characteristic for the S and Y. Use this formula, we can compute the torsion for the product space. Also, it is only true for the normalized inner product, but we have formula between the normalized product, the torsion between these two inner products. So from this T prime, we can compute the T. Actually, we have also a formula for the T for the standard product. We will show you later. This is the idea. We give us an idea how to prove this formula. For given lambda is the eigenvalue of this Hodge Laplacian delta p, where this is the eigenspace EP. Lambda is the eigenspace for this lambda p and delta p, and the EP prime and the EP double prime is the subspace of the EP. So you can prove actually this EP is the direct sum of these two subspace. And this is the first factor we need to use. And the second factor is this isometries between this EP double prime and the EP minus 1 prime. These two subspace. Use this operator. And this lemma is true for any simplex complex. So it is not only for the path complex. Actually, this is true for any simplex complex. So, and if you use this notation to NP prime and P double prime to denote the dimension of this space, then we can get this formula. Get this this is Euler characteristic, like by definition, it's just this. And we can also prove this is the sum. This is zero. It's zero. Yeah. This is just use this. The second one just use this. We use this two. You can easily prove this for this vector. Now we use the second one. Second lemma we need to use. This is come from the past complex. This is the Kuhn's formula for the past complex. For the product space Z, we have this Kuhn's formula. This formula I only write for the omega p, but this is also true for the homology group. HP is also true. We have the same formula for the homology group HP. So use these two lemma, we can prove the product formula for the torsions. This formula is for the standard inner product for the omega p. So we have this extra term, this sum for the standard inner product. Given an example for this prism digraph, this is a product of these two graph I and Y. I is the interval and Y is the triangle. So you can compute the torsion for I is the square root of 2, and this for the Y is that. So use the formula the product formula, we get this Z. For Z, his torsion is the square root of 3. For the standard inner product, also we can use this formula. This is for the Cartesian product of the graph. We can also do the similar thing for the join of the past complex. For this case, we need to use so-called augment chain complex. We add some space we called R-1. It's span of this E. E is the empty path by the definition. So I will not tell this in detail. Just we can do what is the join of these two paths for U in RP and V in RQ, and the join is in RP plus Q plus 1. So the join of I0 IP to the Z0 to ZQ is just this path I0 to IP. So this is the definition of the join. Of course, for join also you can define the path complex for the join. And this is also we have this Kuhn's formula for the join. And given this Kuhn's formula, similar we can prove the formula for the join, the torsion formula for the join. So also we need this product formula for the Laplacians for the join. So this is the formula for the join of these two paths to the complex path. This is an example for the join. You start from the digraph to consider to this joint weights. If you join, then you can get this. This is D2 and this D3. You get this graph, and you use the formula for the join, and you get the torsion for this graph D3. The last part I will talk about is spectrum for the Hodge Laplace on the product graph of Gn. So we use this notation spectrum G to denote all the spectrum for Hodge Laplacian delta P from P equal from 0 to infinity. Because on some graph, we can, even the graph is finite, but you can construct some special graph for all the P, delta P is not trivial. So still we need this spectrum from P equal to 0 to infinity to denote all the spectrum of this. Here, delta P is the standard Hodge Laplacian, which is standard inner product. So Gn is the product graph, it's just n time of this Cartesian product of G. This theory was proved a few months ago, which Grigor'yan, Yau, and Han Zhang, he's my PhD student, he's here. And we prove for a finite digraph G, and the spectrum of Gn is determined by the spectrum of G. And the second thing is if omega r is trivial for some r bigger than 2, I just tell you it's possible this is not trivial for any r. So we need this assumption. And then the spectrum Gn is determined by the Euler created delta G and the sequence. This sequence, the spectrum of delta Q from 0 to r minus 2. Use this theorem, we get a corollary. Consider an interval digraph. I is just an integral digraph. There are two weights. There's one direct edges from 0 to 1. And In is the n times a Cartesian product of I. Then this, for example, this is the left-hand side, the picture on left-hand side is the I2, and the right-hand side is the I3. Then you can, we classify all the spectrum of this In for any P between 1 to n. So this is the, this is number, which this is the multiplicity of these eigenvalues. So this means how to say this sum. If they are different, they just sum. If they are same in the two sets, they just sum the multiplicity of them. Yeah. So in particular, the maximum eigenvalue for In is this number, and the minimum eigenvalue is 2. For the multiplicity is this number. Actually, in this paper, we give two digraphs. They have the same spectral set G, but they are not isometric. So because Yao has asked questions, can we use all this spectra to determine the isometry of these two graphs? But we actually find two graphs is not isometric, even they have the same spectral set. So I will stop here. Thank you.
Thank you. Any question?
So when you talk about the path homology satisfies Cartesian product and the Kuhn's formula, that also reminds me there's another homology from algebraic topology, especially used for computational science.
What is?
called cubical homology, defined on cubical complex, also satisfying these properties. So do you think those two things has any other relationships?
But this, your definition is for the complex, not for graph.
Yeah, for cubical, so defined by a product of intervals, so they naturally satisfy the Cartesian product and this formula. So I'm wondering, is this two kinds of homology has any other further sharing any other further properties in common?
I don't know, but the coolness formula to prove the coolness here is actually not trivial. So from this point, I don't think they are same. Yeah, somehow.
Thanks for the talk. Are there any situations where you can get a digraph from a manifold and their torsions will agree?
Sorry.
So are there any situations where you can start, say, with a manifold, obtain a digraph, and then the two notions of torsion will agree?
So you get a grid from the manifold.
So yeah, some digraph from a manifold,
and then you use this. You mean the original torsion from Reidemeister from here?
Both of them should be the same under some circumstance.
For the triangulations, maybe in some though I don't think they are same because the homology group are defined different, completely different.
Okay.
Any other question?
At the end of talk, you mentioned an example that has the same,
spectrum.
But not isometric. So, can you tell us about this example?
This actually just some torus, and actually they are isometric. They are same torus, but which different direction of the edges.
Torus.
Yeah.
Any other question? Okay, if not, let's thank the speaker again.